as Doug said, I'm going to talk about innovative solutions for high-precision CO₂ isotope measurements using our new LI-7825 instrument. So I'm going to begin with an introduction, talk a little bit about why scientists are interested in measuring CO₂ isotopes. So the driver for developing the instrument that we've just launched, an introduction to isotopes and isotopologues, what that means for the measurements, and then I'll talk a little bit, just introduce the instrument itself. So talk about some of the specifications of the instrument and also our internal testing and the performance of the instrument measuring various isotopes. And then perhaps the best way of describing how to use this is to talk about some applications. And these are applications that we tested with the instrument during development. And some of these concluded quite recently, applications including soil measurements using our flux system, atmospheric measurements, looking at source attribution of CO₂ from various emission sources, a forest ecosystem example, where we look at CO₂ buildup above a forest canopy. And then finally, a super interesting study by a group in Italy looking at volcanic emissions and how isotopes can help us discriminate between sources in a fairly crowded environment with other emission points in that same area. So I'll begin with just a few bullet points here, just to describe why are scientists interested in CO₂ isotope measurements. And so there are various reasons. One of those is source identification. So CO₂ isotopes can distinguish between sources like fossil fuels, CO₂ from biogenic respiration, ocean exchange, and also volcanic emissions. And that's very important in, as I say, like a crowded environment where there are many emission sources present. It also gives insights into the carbon cycle. So we can track CO₂ movement between the atmosphere, oceans, and biosphere, and reveal fluxes and feedback mechanisms within that cycle. Climate change studies, Delta 13C data quantifies fossil fuel impacts, ocean absorption, and the response of ecosystems to global warming. Agricultural and ecological applications, Delta 13C there can differentiate different plant photosynthetic pathways, so C3 versus C4 plants, also assess water use efficiency and stress within those systems. And then finally, volcanic systems. So Delta 13C can help quantify volcanic CO₂ emissions and their overall contribution to atmospheric CO₂, which during perhaps a large eruption event can be very significant in a short space of time. I should just give a short introduction into isotopes and isotopologues, the difference between the two, and the terminology that we'll use in the presentation. So isotopes are different forms of the same element that have the same number of protons, but a different number of neutrons. So for example, we're very interested in carbon-12, carbon-13, both of which are measured in with this instrument. And you can see the carbon-12 nucleus has 6 protons and 6 neutrons. So it's giving you the 12 mass, whereas carbon-13 has an additional neutron. So it's just one more mass element than in the nucleus than the carbon-12. In terms of the chemistry of the molecule containing these isotopes, it's exactly the same, but the difference in mass does affect different physical processes. We use the term isotopologues occasionally, and these are actually molecules that differ only in the isotopic composition of one or more of their atoms. And so they have the same molecular formula, but different isotopes of one or more elements. And you often hear the two terms interchangeable, and perhaps isotopes is more familiar to describe both the elements and also the molecules. So we'll use that isotope terminology unless there's a specific reason to use the term isotopologue, just to hopefully keep things more familiar to people listening. So what are we measuring with the instrument? We're measuring different isotopes of CO₂. And so you can see here the relative abundance of those different isotopes. CO₂ is predominantly the C12, which is O16, C12, O16. And you can see almost 99% of the CO₂ in the atmosphere is this particular isotope, and 1% being C13. And then the O18, O17, progressively less abundant, so very, very low concentrations of those isotopes in the atmosphere. So quite a challenging measurement using any kind of technique, but we've managed to do that with the cavity enhanced absorption spectroscopy using optical feedback in the LI-7825. It's worth featuring and trying to describe the measurement scale, the way that these measurements are reported, and it's perhaps slightly different if you're not used to dealing with isotopic measurements. The delta 13C value is a measure of the relative abundance of stable carbon isotopes, so C13, C12, for example, in a sample. And the way that's reported is to compare that to a standard reference material. It is expressed in parts per thousand or per mil, and calculated by the formula you see there. So it's looking at the 13C to 12C ratio of a sample divided by the same ratio for a given standard. And that standard is historically a physical standard, a carbonate sample that's digested to release CO₂ with a known isotopic ratio. There's a very good reason for using a standard rather than making a direct comparison of isotopic ratios between samples. It can be very challenging, and that's for several reasons. So firstly, isotopic ratios are very small. The absolute abundance of 13C relative to 12C is very low, around 1.1%, and that makes a direct ratio value comparison difficult to interpret meaningfully across studies. So for example, a delta 13C of 0.1 per mil is the difference between 0.0112372 and 0.0112361. So you can imagine trying to express that and compare values from study to study is not very transparent. And so expressing those differences relative to a standard provides a more practical and comparable scale. This is also highlighted in the need for consistency across studies. So if you're comparing just direct ratios from study to study, that's influenced by potentially the laboratory experimental technique or the calibration protocols in place. But using those ratios referenced to a standard means that those values can be compared like for like from lab to lab. And then finally, highlighting relative differences. So delta 13C expresses the difference between the sample and the standard, which is much more relevant for understanding and interpreting processes like photosynthesis, respiration, and carbon source contributions. And that's very evident if you look at the scale visually and where samples sit on that scale. So you can see here, I mentioned that physical standard, and that in this case is Vienna PD belemnite, which is as I say, like a physical artifact that produces CO₂ with a known isotopic ratio, and that's deemed to be 0 on our scale. And then any changes relative to that standard can be clearly seen in the scale, and you can see now we can compare very readily from different sources. For example, CO₂ related to C3 and C4 plants can be easily distinguished, as can derivations of those plants, crude oil, coal, wood, for example. And then volcanic CO₂, you can see to the right here, a very, very different isotopic signature relative to the standard. And we'll see how that's used in those practical examples and those case studies where these differences can be clearly used to discriminate the sources. I mentioned that the CO₂ in terms of chemistry is exactly the same regardless of the isotope. So chemical reactions remain unchanged. So electronically it's identical, but the difference in mass does affect certain physical processes. And I'll give just a couple of examples. And this is a nice simple example. If you think of CO₂ dissolved in the ocean, and then that enters the atmosphere through gas exchange. That process prefers a lighter isotopic CO₂. So the lighter the CO₂, the more readily that would then move from water to the atmosphere. And so the consequence of that is that the atmosphere becomes enriched in C12 or depleted in 13, and so you get this more negative signature, while the ocean becomes enriched in C13 and depleted in C12. And so there you can see a positive delta because of that enrichment of C13. So that's a very simple example just based on energy input into the system and the difference in mass between those two isotopes. Another very useful example, which comes into play with any kind of substance derived from plant material, is the fact that the two different photosynthetic pathways, C3 and C4, process C12 and C13 in different ways, very clearly affecting the isotopic signature. So, for example, in C3 plants, isotopic fractionation is dominated by carboxylation, reaction of Rubisco, and so very much more C12 is taken up in the plant, preferentially to C13, whereas in the C4 photosynthetic pathway, isotopic fractionation is dominated by CO₂ diffusion. It's still preferential to C12, but not to the same degree as the Rubisco reaction. And so what you see on this plot on the right-hand side very clearly is a distinct difference in isotopic signature between C4 and C3 plants. And we'll see how that, again, can be used to discriminate sources from fossil fuel emissions, for example. Moving on to the instrument, if you're familiar with the trace gas analyzer platform, you'll see and you'll notice that this looks exactly the same as our concentration instruments for N2O, for methane, CO₂. It's based on the same technology, the same low power portable solution, and it's capable of measuring the four most abundant CO₂ isotopologues, so 12C, 13C, 18O, and 17O. And this can be used in the field, like our other trace gas analyzers, or in the laboratory. It has high enough precision to be comparable to typical lab-based instruments using optical and other techniques. It also reports delta 13C, delta 18O, and delta 17O using that VPDB standard that I mentioned. It also reports and measures ammonia concentration. This is typically, or this is specifically for interference correction, but we do report ammonia. So you do get an ammonia concentration reading from the instrument. And again, ammonia emissions can be correlated with other sources. And so this instrument can be useful, or that ammonia report can be useful for certain applications. It can be used in conjunction with our soil flux system, which we'll describe in detail, used for ambient monitoring, lab-based measurements, with some adaptation, plant physiology applications, dissolved inorganic carbon, and also isotopic measurements can be applied to other applications such as mud logging, food adulteration, and point of origin. It's a very versatile instrument. Look at some of those key specifications, a wide operating measurement range in terms of CO₂ concentration, fast response time, based on the low volume of the system. And as you can see, extremely high precision for CO₂ concentration, as well as delta 13C, 18O, and 17O, for example. Delta 13C down at 0.04 per mil with 5-minute averaging. Also very low drift, so that does mean that calibration interval, depending on the application, can be long. But as we'll perhaps describe, I'm sure you have questions about calibration. It's very largely dependent on the demands of the particular application and what the degree of changes per mil that you need to resolve. For the ammonia measurement, it has a very wide operating range, up to 30,000 ppb, still 1 Hertz measurement rate, with a precision of 2 ppb with 1 second averaging. While it's not a fast ammonia instrument in terms of gas transport, it's not optimized for NH3 transport. The performance is comparable to currently available portable instruments using laser spectroscopy. So it can be used for studies like cattle barn applications, agricultural use where you're seeing quite high emissions. Looking at several Allen deviation plots here, just to show you the effect of that long-term stability. You can see in terms of drift per mil, just around 6 per mil over a 9-day period. And then in terms of short-term precision, you can see in 1 second we're getting less than 0.3 per mil precision, and with 5-minute averaging down all the way down to 0.02 per mil with this particular instrument. So significantly better than our specification, which is quite conservative. For delta 18O, less than 1 per mil in 1 second, and less than 0.1 per mil in 5 minutes. And quite unique to an instrument of this type, we also do report delta 17O. So we're measuring the fourth less most abundant isotope. And so we report delta 17O with a short-term precision of around 3 per mil in 1 second, down to around 0.2 per mil in 5 minutes. Because we're measuring all 4 of those major isotope logs, it is also reporting a very highly precise and potentially accurate CO₂ concentration. So our LI-7815 instrument, which is our current high precision CO₂ concentration instrument, simply measures the C12 line and then reports total CO₂ based on natural abundance of those other major isotope logs. So they're not actually measured. So any deviation from that in the sample could affect the reported CO₂ concentration. But with this instrument, because we're measuring those 4 isotope logs, it does provide you with a much higher degree of precision, particularly in samples where there could be unnatural variations in C12 and C13 isotopes. In terms of general specifications, as I mentioned, exactly the same as our 7810 methane instrument, 7815 CO₂, and 7820 N2O instrument, based on the same optical feedback, cavity-enhanced absorption spectroscopy. The total weight of the platform is just over 11 kilograms. Very wide operating temperature range, that doesn't change. That's still minus 25 to 45, so we can use this outside in a variety of environments very comfortably. And power consumption as well is the same as our other instruments. So we get 8 hours typical running with 2 fully charged batteries in the system and a steady state operation power consumption of just 22 watts. So very field deployable. I'll move on just to describe several applications for CO₂ isotopes, and these examples are based on beta tests of the instrument during development, and we had some great groups that were willing to both do the work with the instrument and also allow us to share that with our customers. And so we've tried to cover as diverse a range of applications as possible ahead of launch. And I'll begin with some internal testing with our soil flux systems. So before we launch the 7825, this is a kind of typical setup that you'd need in the field to get isotopic measurements of CO₂ from a soil system, so from a chamber. And as you can see, I won't name the instrument, but many will be familiar. But there are other instruments of this type that would require similar infrastructure. So you need, typically it's a mains powered laboratory instrument. You can see this one requires a monitor to actually operate the instrument in the field. It will need only be able to be used during certain weather conditions. So these instruments are not weatherproof, can only be used in a very narrow temperature range, typically like a laboratory setup, so maybe 10 degrees or 5 degrees up to 30 degrees C. So definitely not ideal in quite a wide range of environments and temperatures. And you can also see just a lot of infrastructure, heavy instrument that needs to be taken to the field, but it always has to be quite close to, I'd say, that mains power supply. So not very practical, but scientists have made this work over the years. And so moving to a 7825 to do this kind of work is a huge leap for this kind of research. And so now for our soil flux systems, we've now fully integrated the LI-7825 into those systems, and the hardware is now available to get up and running in the field for long-term measurements. And we can use the measurement of CO₂ isotopes there in that setting to characterize the source of the CO₂. The key components of this system are, of course, the LI-7825, the gray box, and then a series of long-term chambers connected to the instrument via a multiplexer, potentially extension manifolds to increase the number of chambers from 8 to 36. And one of the key components that we've developed for this fully integrated system is the LI-8250 O2 calibration manifold, which is the smaller yellow box you see in the middle here. Looks a lot like our 870 CO2 instrument. And so this box provides in the field automated calibration. So it allows a daily automated zero of the instrument to correct for zero drift, which is the major drift in the measurement. And a daily zero is sufficient to maintain stability of the measurement and the accuracy of the measurement. The other issue we have to deal with, and this is common across all optical instruments, not just the LI-7825, but all cavity-enhanced systems, for example, FTIR, and other, is the handling of water transients. So the delta 13C measurement is affected by transients in water vapor, and that build up in water vapor in the system and the change in concentration over the duration of the measurement. And so that's accounted for using a dryer buffer system within the system, which removes water to a consistent level during the course of the measurement. This is only available for our long-term systems currently, not for the smart chamber, simply because of the buffer system, which requires a power source from the 8250 multiplexer. But it's something that users could mimic for a smart chamber measurement, although there's not full integration in terms of data processing and data reporting. So a quick look at our field study to validate this measurement and the system. On the right-hand side, you can see a schematic of the setup. So we've got our LI-7825 isotope analyzer connected to the multiplexer via the calibration manifold. And you can see the calibration manifold is connected to a zero air, a CO2-free air cylinder. So each day, that gas is used to zero the instrument and maintain accuracy of the measured delta value. You can see we've been able to run this system in parallel with our LI-7810 methane analyzer and also our LI-7820 N2O analyzer. So you can connect all three instruments via the multiplexer with data collected and processed in real time as it's bringing in gas from the various chambers connected to the system. And you can see that clearly on the photograph on the left. There's our chamber, multiplexer, extension manifold, and the calibration module. And the analyzers are housed in these small animal shelters just to keep off direct sunlight during summer and rainfall during any downpours that might occur. So that's a very low-cost way of protecting the instrument in the field. And these systems can run 24/7, 365 days a year. In Nebraska, for example, where this is located, we can experience temperatures across that full operating temperature range from -25 to +40. So it's a very good demonstration of the robustness of the system. So what do we collect? What data do we collect with the system during the measurement? We obviously collect CO2 concentration to calculate flux, but with the 7825, we're also looking at the measured delta 13C values. In this case, from 4 automated chambers from that system that I showed you. So in the first week, which is this section to the left, you can see data collected over untreated grassland plots. While in week 2, the section on the right here, we show one plot dosed with C3 soybean residue, which is the blue plot here, and another with C4 maize residue, which is the green dots at the top, while the grey points remained on the bare grassland. And what you can see is a clear differentiation in measured delta 13C based on the C3 and C4 photosynthetic pathway. And those values do correlate very well with, and they're consistent with those associated with C3 and C4 plants. So approximately -28 for the blue, which is the soybean residue, and approximately -13 for the C4 maize residue. Now, what we're really trying to learn from this measurement is the delta 13C from the source. So you can imagine as we close the chamber, we've got delta 13C associated with background air or background CO2 around -8. And then CO2 from the soil is then diffusing into the chamber with a different delta 13C value. So gradually there is a change in the overall delta 13C for the period that we collect the data. So you can see here the data set at the top right. But what we want to calculate is the value of delta 13C at this y-intercept. And so we've got two ways of doing that. And the traditional way to do that is to use what's called the Keeling method. And that involves fitting a linear model to the relationship between delta 13C and the reciprocal of total chamber CO2. And you can see as we plot that line and calculate the y-intercept, we get a delta 13C value of 22 or -22.1 per mil. And that is the delta 13C of the source CO2 coming into the chamber from the soil. And we have an alternative method to do this, which is a bit less sensitive to analyze a baseline drift. So that offset that can occur, this method is impervious to that offset. And this is called the slope method. And what we do here is we plot basically delta 13 CO2 versus 13 CO2 versus 12 CO2 concentration over time, and then we calculate the slope of that change, and then divide that by the standard -1 times 1,000 to give us our source delta 13C. And you can see the two values. So using the Keeling method, we've got a value of -22.1, and then for the slope method with the same data set, we get a value of -21.1 per mil. So very close with that slope method preferred in terms of dealing with baseline drift. I mentioned the handling water transients with the 8250 O2. And so we set up an experiment here, which is a Keeling regression of a controlled flux. So 0.65 micromole of CO2 per second into the chamber. The background gas having a delta 13C of -13.7 per mil. And we generated a flux by injection of pure CO2 with a delta 13C of -36.7 per mil. So a very different value there. What you can see are two different plots. The blue circles are associated with gas passing through the 8250 O2 vapor equilibrator or buffer, whereas the green triangles show the same experiment without equilibration, so without that buffer. And what you can see is with the plot in the bottom right here, this is the change in water vapor during that process. If there's no buffer, and the blue line is if the buffer is in place. And you can clearly see the effect on the data if we don't use the buffer. You can see this deviation from the fit very, very clearly, which will affect your calculation of delta 13C for the source. So it's a very important addition to the system and a key component that has to be deployed with the long-term chamber system. The other issue that we have to deal with that I mentioned is ammonia interference, and that can be present in a variety of situations, for example, in an agricultural setting. But this is a nice example that was discovered during the experimentation. What you see here is estimated delta 13C from seal volumes containing soybean, which is the blue plot there, and maize, which shows the green data points. And this is with no spectroscopic correction for ammonia. So we haven't applied the correction in this case. And what you can see is that during decomposition of the soybean, there's no release of ammonia. And so the observed delta is consistent and reliable. But during decomposition of the C4 maize, you're getting off-gassing of ammonia during that decomposition. And that's skewing the delta 13C to wildly unreliable values, right up to over delta 13C of 130 per mil. So unrealistic values. And that's as a direct consequence of that ammonia interference. And so the instrument now does measure ammonia, reports the concentration, but is also incorporating that into the spectroscopic fit and eliminating that interference. So we can continue then to report CO₂ isotope logs and delta 13C with high accuracy. I've described our our solution, the LI-COR solution, which is fully integrated and tested. But of course, we do have quite a number of customers using custom chambers and custom systems. So we have to stress to them to consider the same issues that we've overcome in the development of our system. That includes CO₂ sensitivity, so that daily zero calibration should be implemented. Customers will also need to dry the water from the gas stream or find a way to keep water constant to avoid that dependence on water concentration change. And also another issue, depending on the materials and components used in the system, there could be fractionation, so preferential perhaps a leak of C12 versus C13, for example, across certain materials. So we've tested thoroughly the system that we manufacture and supply, but it's quite possible that in constructing a custom system, you might use a material that actually invokes quite a large fractionation and can affect your measured your data. Also, the slope and the Keeling methods to derive delta 13C from the source CO₂ are built into our SolFlux Pro software, so that's calculated and reported in the software. If you're using a custom system, of course, then that data will need to be calculated manually post-process. Look now at atmospheric measurements. Obviously, the instrument was designed for portable use, but because of its performance, it does bring opportunities to expand on laboratory atmospheric measurements due to its design and high precision. Should stress across all applications, calibration protocols are dependent on the demands of the application. So for long-term monitoring, for example, it may need more frequent calibration to be able to discriminate smaller changes in delta. And so that those calibration frequencies are much higher than expected for our concentration analyzers, which much less demanding instrument in terms of long-term drift. So a very nice example that was carried out by a beta test customer, which was the Scripps Institution of Oceanography in California. They installed a LI-7825 at the end of their pier, which you can see in this photograph in the bottom left. And that's located just a fair way south of Los Angeles, but in super sort of mega city area, very high potential for emissions from Los Angeles to make contact with La Jolla, as well as the San Diego area as well. So there's a lot of potential here for combustion, fossil fuel sources of CO₂ emissions. And that's really what this group is interested in doing, is interested in measuring CO₂ concentrations long-term, but also to attribute any pollution events to particular locations based on wind speed and direction and isotopic measurements. And so what you see on the right-hand side are a number of plots. The top plot here shows these sort of brown crosses are calibration tank measurements, so consistent measurements over that sort of 2-week period. And the blue plot here is CO₂ concentration. And we might assume that these are related to pollution events because they're much, much higher than background. But if you look at the plot below, we can confirm that by the change in delta 13C that's measured associated with those events. So if you recall, the delta 13C value associated with fossil fuels is significantly more negative than a typical background, which is around, in this case, about -6. But you see these excursions down to -8, -10 as those pollution events occur and the fossil fuel emitted CO2 passes through the sampling area. And sort of circling back to that C3, C4 plant example, because fossil fuels are derived from ultimately plant material and the reaction and degradation of that material over millennia, they still maintain the same isotopic ratio for associated with C3 and C4 plants, and which is why fossil fuels show this very negative delta value, which is apparent in these atmospheric samples. Next example is another nice study. This is by a group in Royal Holloway, University of London. They have a forest site in south of England, and they have a relatively tall tower which protrudes through the top of the canopy, and they're measuring CO2 above the canopy, and they're interested in what's happening through the diurnal cycle. So, for example, during daytime, photosynthesis dominates and CO2 concentration above the canopy decreases, which you can be seen here during the daytime period in the top right-hand corner, down at sort of background level, 420 ppm. And then during nighttime, photosynthesis ceases in the absence of sunlight, and then respiration dominates. And so the CO2 concentration above the canopy increases to up to like 560 ppm. And trees release CO2 derived from the breakdown of organic matter stored during photosynthesis. So again, that more negative, more preferential uptake of C12, the lighter isotope, which means that the respired CO2 is also isotopically lighter with a lower delta 13C value compared to atmospheric CO2. You can see that quite clearly in the plot bottom right, and also from this example from the literature, the reference at the bottom there, you can see the projected source CO2 there, the delta 13C below -25. And then the final example I want to give is a study by a group in Italy, INGV, and this group is engaged with long-term monitoring of volcanic activity in various locations in Italy, with this group focusing on Sicily and the island network around Sicily, including Stromboli, Vesuvius, and in this case, a small island called Vulcano. So the actual island is called Vulcano. And here, some very nice work. They used LI-7825 in a vehicle to map emissions around the volcano crater, essentially. And so the delta 13C of volcanic CO2 reflects a mixture of mantle-derived carbon and contributions from subducted carbonates or crustal rocks. And the typical delta 13C values observed there are around -4 per mil to +2 per mil. And so that's compared with typical atmospheric delta 13C of around 8 per mil, or associated with fossil fuels ranging from -44 to -19 per mil. It's also interesting to note that ammonia is associated with volcanic activity. So for this instrument, that ammonia measurement becomes important, and that's associated with thermal decomposition of nitrogen-containing compounds and other reactions that are going on below the surface with magmatic gases and water and geothermal vents. And so you can see some very big variations as the group drives around the volcanic area. So look at, for example, this area. First of all, we can see CO2 concentration very high, this sort of red area up at 500 ppm. And if we then look at the isotopic ratio here, more negative in this area, and that definitely is a strong indication of fossil fuel combustion from transport, so from cars and buses, etc. And sure enough, this is the town area or the major urban area, very close to the volcano. So a thriving tourist town where you would expect to see this kind of emission. That's confirmed in the drive around. And then obviously a strong interest is to discriminate the volcanic sources from those fossil fuel sources and others. And sure enough, using this instrument, we can discriminate those sources very clearly. So we've obviously got a higher concentration of CO2 than background, up towards 480, 490 in some cases in these locations, the orange bands. If we look at the isotopic ratio, then these orange areas in this region are less negative. And so that's the contribution of volcanic delta 13C to the overall CO2 in the atmosphere. And so very clearly, just using these drive round studies, the group is able to discriminate between fossil fuel CO2 and volcanic CO2. And that's also confirmed by much higher than background levels of ammonia. And you can see all through this area where they're driving and sampling, you get a much higher than background ammonia concentration. So very clearly, they can use this system to monitor this over time. And this is changing month to month. The group ultimately wants to measure this month to month to try and understand what's going on below the surface, that volcanic activity. Okay, so in summary, we've introduced CO2 isotopes and why they're of interest to scientists investigating aspects of the global carbon cycle, provide an overview of the 7825 CO2 isotopes trace gas analyzer, and finally demonstrated use of the instrument in soil applications, atmospheric monitoring, forest ecosystem site, and also for volcanology groups looking at volcanic emissions. Okay, thank you very much, and thanks to my colleagues that helped put this information together and to help with the presentation today. Thank you.
All right. Thanks, Graham. So for anybody online with questions, feel free to add them to the Q&A, and we'll try to answer those. And a couple of them maybe we have a few minutes here for questions. We'll probably go through a couple of them live here, and the rest of them, if we don't get to your question, we will certainly write you an answer at some point. So a question here that I think I'll address is a question about measuring small gas samples, potentially a leaf chamber with a photosynthesis system, or CO2 released from small soil samples, soil incubations. And both of those applications are certainly possible. Both would be extremely challenging applications, and considerations of the full setup are really important. So things that Graham touched on, such as changes in water vapor, can be critical for both of those applications and would need to be dealt with. Calibration frequency will be something to consider. So yes, theoretically, those are both absolutely possible applications. Signal to noise is another issue. As Graham showed, we have pretty good performance, but you need to make sure that the signal you're trying to measure is outside of the noise of the measurement. But yeah, that's a great question. Let's see. As I was answering that, another question might have come in. See if I can. Oh, they're getting answered by Lu Kong and Sasha and disappearing from my screen here. There was one earlier regarding data rates and data storage that I'll go ahead and address. So the native data output rate of this instrument is 1 Hertz. And onboard memory can store a couple of months worth of data of that 1 Hertz data. So I'll just knock that question out. And there's a question. Let's see, Graham, maybe I'll let you address this. Let's see, there's a question about high altitude. Any particular issues with that besides going into the high altitude mode?
No, I don't think. No, I don't think so. Is my initial answer. That does broaden the inlet pressure, I think that was a question that appeared and disappeared, but that does, reduce the lower limit there. I think from 70 kPa to 50 kPa.
Yeah, that's right. That's my understanding as well. Yeah.
Yep.
All right. Here's another question on minimum fluxes in the soil application to get accurate representation of the soil delta 13C. So yeah, a minimum detectable flux essentially to get a good regression. Lukong, do you have a good answer there? I don't know if we have that particularly defined, but maybe Lukong, you want to speak to that?
No, I don't have on top of my head. But when you do the killing plot, you need a little bit range of CO₂ to get the killing curve. So I have to think about it and come back to mailing later.
Okay, great. Yeah, I don't have a kind of rule of thumb number in my head either for that. Here's a question on the calibration module, the 8250-02. So it's asking, does the span also need to be calibrated? So I think, Lukong, do you want to address that, or do you want me to?
You can do it. Go ahead.
Okay. Okay. Yeah, this is a great question. So the majority of the drift in this analyzer is in the a zero shift. So a well-calibrated analyzer to start will drift over hours to days, and most of that drift can be accounted for in the change in zero. So a short-term operation, meaning daily, resetting the zero does a good job of keeping drift very, very small. Now, that does not mean it never needs to have the span adjusted or at least checked, but that can happen at longer time intervals, weeks to months. So I think that's at this point, the best recommendation for use with this analyzer is we have this automated zero operation in place for that particular application, which is extremely useful and I think necessary. And a periodic span check by the user is a good idea. And then that span check can happen, like I said, at weeks to months. We've seen it be very stable. Yeah, that's a good question. And I don't know if Graham, if you want to chime in more on that, or.
No, I think that covers it very, very, very clearly. We didn't talk about calibration from a factory perspective, but we can share further details with attendees at a later date on that topic.
Yeah, that's great.
Yep.
All right, let me see. Did I miss any here that we didn't address? A couple got answered while I was talking. Let me see if I missed any. Got that one. That one.
I think Lukong just addressed something about temperature range and water, potential water ingress.
Yes, there it is. Limitations, high temp or rainfall. So right, Lukong put the answer there, but I'll go ahead and state it that the operating temperature range is minus 25 degrees to 45 degrees Celsius. Yeah, liquid water is obviously not a desirable outcome in any optical flow path and will cause damage. So you do have to protect from rainfall. And I think maybe you can go back to that slide, Graham. There's some nice pictures of some kind of easy ways to weather protect these analyzers in the field using those plastic huts. Let's see, he's going back.
Yeah,
now.
exactly,
There we go. Yep.
Dog house.
Yes, yeah.
Yeah, those are nice solutions to protect the analyzers from the elements.
Yep.
Well, I think that's all the questions I see. So, Graham, thanks very much. And then anybody, still listening, if you have further questions that come up, feel free to contact us later. And if it hasn't been said, this recording of this webinar will be, or a link to it will be emailed to you, so you'll have access to it in future. And with that, we will close. Thanks, everybody. Have a great rest of your day or evening.